Hello. So today I'm going to do section 1.2 and finish that up. But before I do that, let's look at the example that I looked at in the question that I got last week or a few days ago, which I uploaded. I'm sure you guys remember this if you watched the video. The mistake that I made was right here. When I added 2 plus R2, I should add I should do R3 plus 2R2 here, and here I should add 1 plus 2 times 3, which should equal 7. And here I wrote 5. This is wrong. It should be 7. So if I change this to 7, then when I do R4 plus 3R3, I will get R4 is negative 11 plus 3 times 7, which is negative 11 plus 21, which is negative 10. So this number here should be negative 10, and this number here should be 7. Okay? So from this equation here, this one, we get negative 5x4 equals, this should be positive 10. So when I divide by negative 5, I get x4 equals negative 2, which is the correct answer. And then you finish this up like the way I asked you to, by changing these to zeros, and you should get x3, x2, and x1. Okay, this is wrong. It should be 10. Okay. Okay, so today we're going to start section 1.2. And it is called row reduction and echelon form. Okay. In this section, we're basically going to show you, when you have a system of linear equations, 3 equations, let's say, okay, and you turn this into a matrix, right, with columns and rows and then the equal part here. How do you use this to find the solution? In section 1.1, we did a few examples, but I didn't give you the rules which show you for every system how to take the matrix and find the solutions. And in section 1.1, we found out that any system has either 0 solutions, 1 solution, or infinitely many solutions. And we also looked at a 2-dimensional case where we saw what a solution is an intersection for 2 lines, and for 0 solutions we have something like this. For 1 solution we have, the 2 lines intersect. Right here is the 1 solution. And then for infinitely many solutions we have the lines are on top of each other. Okay. We're going to see what that looks like or what that means in 3 dimensions as well. But first, let's show you how to take an augmented matrix. This is called an augmented matrix. How to take an augmented matrix and to find the solution using what is called row reduction. Okay. So first, let's start with two definitions. A leading entry in a matrix is the leftmost non-zero entry. What does this word leftmost mean? It means the one that's the most to the left. Okay, so we'll see what that means. So what is an entry of a matrix? Well, if I have a matrix 1, 2, 2, 1, 3, 3, each of these is called an entry. This is an entry, this is an entry, this is an entry. These are all called entries, okay? And the leftmost entry is the entry that's the most to the left in each row. So this is the leading entry in row 1. This is the leading entry in row 2. But if I had a matrix if I had the following matrix, then the leading entry in row 1 is 1. The leading entry, remember, the leading entry has to be non-zero. Okay? So this cannot be a leading entry. This is not a leading entry because it's 0. This is the leading entry in row 2. And in row 3, this is a leading entry. Okay? So what is a leading entry? It's the entry in the row that is the most to the left, which is not 0. Okay? So the leading entry here is 1, the leading entry here is 1, the leading entry here is 5. A m by n matrix has m rows and n columns. These are rows, these are columns for a matrix. In this matrix, this is 3 by 3. Okay? Because we have 3 columns and 3 rows. Okay. An m by n matrix is in echelon form if it has the following three properties. 1, all non-zero rows are above rows with all zeros. So for example, if I had 1, 3, 2, 2, 0, 0, 0, 0, 2, 3, 3, 5. This is not echelon form. But what you can do is you can interchange these two rows. Remember, these are elementary row operations. Remember the 3 row operations that we can do? This is one of them. So that I get 1, 3, 2, 2, 2, 3, 3, 5, 0, 0, 0, 0. So the condition number 1 here is not met. But condition number 1 here is met because you see the 0 row is on the bottom. Okay? And everything above it is non-zero rows. So for a matrix to be echelon form, condition number 1 means that the row with all zeros has to be at the very bottom. Or it has to be below any non-zero row. For example, I can have 0, 0, 0, 0, and this is okay as well. This meets condition 1. These are both rows of 0, but because they are below this row of non-zeros, then it meets condition 1. Condition 2. Each leading entry of a row is in a column to the right of the leading entry in the row above it. What does this mean? Okay, this means that if I have a matrix, the leading entry here, let's say it's right here, let's say it's right here, okay, then in this row, the leading entry cannot be here, okay, because the one in the row above it is here, this one has to be to the right. It has to be here or here. Here or here. Okay? So for example, if I had 2 here, 0, 5, and I had 0, 3, 2, then the leading entry is to the right of the leading entry of the row above it. Okay? So we need the leading entries to look like this. Okay? It needs to be like this, not like this. And we'll see examples so that you know what I mean. And we have that all entries below a leading entry are 0. What does this mean? This means if I have a matrix and I have 3 here, 2, 1, and then I have 0, 4, 5, then everything below it needs to be a 0, below this leading entry. So I have to have 0 here, I have to have 0 here, and then here below this leading, because this is the leading entry, below it I have to have 0 here, and then this could be a leading entry or it doesn't have to be. So in this case, condition 3 is met. Okay, but if this was a 3, then condition 3 is not met. Because 4 is a leading entry, everything below 4 needs to be 0. And because 3 here is a leading entry, everything below it needs to be a 0. Okay? And if conditions 1, 2, and 3 are met, then the matrix is called echelon form. Okay? So an example of an echelon form matrix is this. This could be any number. And then I have, and then everything below this leading entry needs to be 0. So 0, 0, 0. And let's say I have a leading entry here. So everything below this needs to be a 0. And then these two don't even have to have leading entries. You see, no leading entry, no leading entry. But condition 1 is met. You see, all of the rows that are 0 are on the bottom. Condition 2 is met. You see, this is a leading entry, and it's to the right of the leading entry in the row above it. Okay? And condition 3 is also met because we have all entries below a leading entry are 0. Here's a leading entry. This is everything below it is 0. Here's a leading entry. Everything below it is 0. Okay? So this matrix is echelon form. And it doesn't matter what numbers these are. This could be 2, 3, 2, 1, 5, 4, 0. Okay? Then this is an echelon form matrix. All right. Another example would be the following. Okay. We see where the leading entries are. Everything below it is a 0. The next leading entry, you see in this column there is no leading entry. Only in this column there's a leading entry. And we see that everything below it is 0. And all of the, you see, all of the leading entries follow a staircase shape. In fact, this is why it's called echelon. Echelon refers to a staircase sort of hierarchy. Okay? And we see that all entries below a leading entry are 0. And there is no rows with all zeros. So this is echelon form. Okay? Now, Furthermore, if an echelon form matrix is, also has the following two properties. For the leading entries are all ones. And 5, the leading entry only has zeros above and below in the same column. So, these two matrices are echelon form. To make them reduced echelon form, we need to make sure that these two conditions are also met. So the leading entry here needs to be a 1. And then everything above it needs to be 0. So this needs to be 0. And in this case, this is now a reduced echelon form matrix. And similarly, if we make this a 1, and then we make this a 1, and then we'd have to make this a 0, this would be a 1, this would be a 0, this would be a 0. 1, 0, 0, 0. 1, 0, 0, 0, 0. Then now this matrix is a reduced echelon form matrix. Okay? And these numbers here could be anything. All right. Let's look at an example. Actually, before we look at an example, let me just say this so that you know why echelon form and reduced echelon form are important. This is called Theorem 1. Every matrix is row equivalent to exactly one row reduced, I should say one reduced echelon matrix. What does it mean to be row equivalent? It means that we use elementary row operations to go from one matrix to the other, and this is reduced echelon. So every matrix we can turn the matrix into reduced echelon form by using row operations or elementary row operations. Okay, and every matrix can be changed to only one reduced echelon form matrix. And what does it mean for them to be row equivalent? it means that the solution for this matrix is the same as the solution for this matrix. Okay? So basically, if we have a system of equations, we change it to a matrix, we use elementary row operations to change the matrix to reduced echelon form, and then it should give us the solution easily. Okay? So let's see how, by following an example. Let's say I had the following. If I had 4x1 minus 3x2 plus x3 equals negative 10, 2x1 plus x2 plus 3x3 equals 0, and negative 1x1 plus 2x2 minus 5x3 equals 17. This is a system of 3 equations with 3 variables, x1, x2, and x3. Okay. You should easily be able to change this into a matrix. 4, negative 3, 1, negative 10, 3, 1, 2, negative 1, 2, negative 5. Okay. Now we want to change this. We want to make it into reduced echelon form. To make it into reduced echelon form, first I have to change it to echelon form, and then I have to change it to reduced echelon form. Okay, so to change it to echelon form, I need this to be leading 0, and then below it, the leading 0 needs to be to the right, and then below it, the leading 0 needs to be to the right, and everything below a leading 0, I need to make it, or I'm sorry, everything below a leading entry, I need to make it a 0. So here's the leading entry, here's the leading entry, everything below it, I need to make it a 0. Or I need to make it look like this, where here's the leading entry, everything below it is a 0, here's the leading entry, everything below it is a 0. So, the only thing I can do to make this reduced echelon form is elementary row operations. Where I can add rows together. I can replace one row with the row plus 5 times another row, let's say. Okay? I can do things like this. What I cannot do is I cannot add columns. Okay? So I cannot say negative 3 plus 1, 1 plus 3, 2 plus negative 5. This will not work. What I should try first is I should have this as a leading entry and then try to make the ones below it 0. But because I see this negative 1 here, I can easily multiply replace row 3 with negative 1 times row 3. And when I do that, I get 4, negative 3, 1, negative 10, 2, 1, 3, 0, 1, negative 2, 5, negative 17. Why did I do this? Because I want this one to be a 1 so that I can now just interchange these two rows. So when I interchange these two rows, I get 1, negative 2, 5, negative 17. I get 2, 1, 3, 0, 4, negative 3, 1, negative 10. Okay? And now I could easily make this one 0. Okay? How? By doing this. Row 2, replace row 2 with row 2 minus 2 times row 1. Okay? Again, why did I choose to make this one a 1? Because it's easy to then make these ones 0. Okay? If this one was a 4, I would have to say row 2 minus 1 over 2, row 1, and then I have to multiply by a fraction, and maybe that makes my calculation longer or more difficult. So it's easier for me to just make the leading entry in row 1 a 1. And then I try to make the ones below it 0. Okay. So if I do this operation here, then I will have 1, negative 2, 5, and then I will have 2 minus 2 times row 1 is 1, this here, and then I will have 1 minus 2 times up here, which is negative 2, and then I will have 3 minus 2 times 5, okay? And when I do that, I get 0, 5, negative 7, 34, 4, negative 3, 1, negative 10. And now I just need to make this 4 a 0. And I do that by doing row 3, replace row 3 with row 3 minus 4 times row 1. And when I do that, I get the following matrix. Okay, so now I have leading entry here. Everything below it is 0. I have leading entry here. I need to make this 5 a 0. Okay, how do I make that 5 a 0? I do row 3 minus row 2. Okay. So when I do that, I get the following matrix. Okay. So now I can do row 3, replace row 3 with 1 over 12, negative 1 over 12, row 3, so that I get 1, negative 2, 5, negative 17, 0, 5, negative 7, 34, 0, 0, 1, negative 2. So now, this is echelon form. Okay? Because I have leading entry, 0, 0. Leading entry is to the right, below it, 0. Leading entry is to the right. Okay? So this is echelon form. Now to make this reduced echelon form, all of the leading zeros need to be 1, and above a leading 0 needs to all be zeros. Okay? So here's how I do that. I can do row 2 plus 7 row 3. Now I'm doing this because when I add this row to this row, because these are zeros, both of these will stay the same and only negative 7 will change. So when I do plus 7 row 3, I will get 1, negative 2, 5, negative 17, 0. This one stays the same. And this one becomes 0. And then I have 34 plus 7 times negative 2, which is going to be 20. And now I can take this row and I can replace row 2 with 1 over 5 row 2. So I get 1, negative 2, 5, negative 17, 0, 1, 0, 4, 0, 0, 1, negative 2. And now I need to make both of these 0. So I can let you finish up this problem, but basically you're going to want to replace row 1 with row 1 minus 5 row 3 so that this one becomes a 0. And then you're also going to want to do row 1, replace row 1 with row 1 plus 2 times row 2, and that will make this one a 0 as well. Okay? And when we do that, we end up getting 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 4, negative 2. And this equation is x1 plus 0x2 plus 0x3 equals 1. This is 0x1 plus x2 plus 0x3 equals 4. And this one is 0x1 plus 0x2 plus x3 equals negative 2. So if we notice, x1 equals 1, x2 equals 4, x3 equals negative 2, which is exactly what's written right here. And this is the reduced echelon matrix. Something else I want to add is if we start with a system and we make a reduced echelon form matrix, which looks like actually let me say this. Let's define something else now too. A pivot in a matrix is the position where a leading one exists in the reduced echelon form of the matrix. So in this case, where the pivots are where the ones are in the reduced echelon form matrix. Okay? Okay. Now, a matrix that is m by n has m rows and n columns. A m by n matrix with n columns has one solution. A column with no pivot corresponds to a free variable. Okay? If a matrix has at least one free variable, then there are infinitely many solutions. And if there is a row like the following, such that, let's say you have a row, and then here you have 0, 0, 0, 5, let's say, or a number that is not 0, then this means that 0x1 plus 0x2 plus 0x3 equals 5, which would mean that 0 equals 5, which is not possible. So if you have a row like this in your matrix, then there are 0 solutions. Okay, so in this lecture, I just gave a lot of definitions, and I used those definitions to explain the concept of row reducing a matrix into a echelon form to find the solution of a system of linear equations like the following. Okay, we did an example so that you can see how you should take a matrix and make it echelon form, and then how you should take the echelon form and make it reduced echelon form. Okay, and we saw that in this case, because there was a pivot in every column, there's only one solution. This is the solution, equals x1 equals x2 equals x3. Only one solution. Why? Is because this is a 3 by 3 matrix, and I've told you right here, if a m by n matrix has n pivots, I'm sorry, this should be pivots, has n pivots, then it has one solution, okay? And this was a 3 by 3 matrix, and so n is 3, and it has 3 pivots, and so therefore this only has one solution. In the next video, I will do an example where we get infinitely many solutions, and I will do an example where we get 0 solutions, so you can see it for yourself. Maybe this lecture was difficult because it had a lot of words that you don't understand and that you need to, sort of memorize the definition of the words. That's okay. But when you see that in an example, it's actually not very difficult to understand the concept. So we did an example here with one solution. We will do an example where we get infinitely many solutions in the next video. And we will also do an example where you get 0 solutions. And then I will show you for a 3 by 3 system, geometrically, what does it mean to have 0 solutions, infinitely many solutions, and 1 solution? Similar to how when we did it for a 2 by 2 system, where we had 2 lines and the intersection of the line was 1 solution. And if we have 2 lines that don't intersect, then that's 0 solutions. And if we have 2 lines that are on top of each other, then that would be infinitely many solutions. So in the next video, again, I'm going to go over examples where we get a system, we reduce it to echelon form or reduced echelon form, and that tells us if it has infinitely many solutions or 0 solutions or 1 solution. And then I will go over an example of a 3 by 3 system and show you what it means geometrically to have 0 solutions, infinitely many solutions, and 1 solution. Okay. I'll upload the next video by Thursday, and I will give you homework which will be due the Thursday after that. Okay? So the homework will be due on Thursday, October 1st. Okay? And if you have any questions, you can contact me. But I'm not going to give you homework for this yet until Thursday, October 24. I will give you homework, which will be due on Thursday, October 1st. Okay? So in the next video, this is video V4. In the next video, V5, I will do this like I explained. And in V5, I will give you homework, which will be due on October 1st. And I will give you V5 on Thursday, October 24.